Guys, do you know how the major databases like MySQL and PostgreSQL work so fast and do fast queries? That is because of one of the data structure which is implemented in them called B plus tree. We do indexing. Because of indexing, we are able to do fast queries, and it's all thanks to a data structure called B plus tree. So today we are going to talk about B plus tree. And no, that's not a grade you got in biology class. It's actually one of the most important data structures in database systems. And after today, you'll be able to understand why every major database from MySQL to PostgreSQL is secretly obsessed with them. Think about a time in 1970s when the computer scientists are storing data in a binary search tree. Life is simple. You want to find something, go left or right, easy peasy. Smaller number, left. Bigger number, go to right. But then the databases started to go very big. And here's the problem. Binary search trees are like that friend who insists on taking the scenic route everywhere. Every search means potentially going down hundreds of levels. And remember, this is 1972. We're using disk drive. Every time you go down one level, that's a disk seek. The disk seek in 1970s were like waiting for your grandma to find your glasses before she can read your text. Painfully slow. So in 1972, B trees were invented, and then B plus trees improved upon them. Think of B plus tree as a Swiss knife for the database indexes. Now let's discuss about how the B tree works, and post that we'll work on the improvement on B tree, that is B plus tree. We'll discuss about the insertion order and how it made life very easy for us. A B tree is an extension of binary search tree. In binary search tree, I label it as BST. We have a root. Let's take an example, maybe 10. The left hand side value will be lesser than 10. It could be 5. The right hand side value will be more than 10. It could be 12. Similarly, B tree can have m number of children. Let me draw an example B tree for you. This is maybe 5, 10. We have 2 members in the root. Then we can have 1, 2, 3, 6, 9, 7, 11, 12, 13. So this is a B tree in which we can have m children varying upon the order of B tree. Let's draw a B tree of the order of 5. So in this case, m will be equal to 5. So some of the rules of the B tree are that the max children in a B tree can be equal to m, and the minimum can be equal to m by 2 seal. So in this case, if we have 5, so the minimum children will be equal to 5 by 2 ceiling. This will be equal to 2.5, which is equal to 3. Similarly, the number of nodes, the number of keys. In this case, the maximum keys can be m minus 1, that is equal to 4. Max keys equal to 4. Min keys will be equal to 3 minus 1, that is equal to 2. Here the difference between the keys and the children is the number of children a parent nodes can have, and keys is the number of values at particular level. If we scroll up in this example, if you see, there are 2 keys here, and how many children are there? There are 3 children. You got the difference between keys and children, right? So this is how we make it. Let's insert some values. In this case, we will insert 1 first, and then because the root is 0, we can insert 1 value. Then we have value is equal to 2. that we can still insert at 2, and then we will insert 3. Because the max key size is 4, we can keep inserting. And one thing to note about is the insertion order in B tree is bottom up. So we will insert from bottom and then move upwards. Next, we will insert value 4. After that, we will insert value 5. But there's a problem here. We've already reached the max. We have already crossed 4. So now we will split and create a parent out of it. To create a parent, we will consider all the values, including the previously inserted and the new value. In this case, the previously inserted values like 1, 2, 3, 4, and the new value, that is 5. Which is the center value out of all of this? It's 3. So our tree will become like this. We will split the tree. So 3 will become the new parent. It will go up, and then we will have two children. One is 1 comma 2. That is the left child, and 4 comma 5. Here we have created a subtree or a new tree. Next, we will insert 6. Since 6 is greater than 5, we will insert it here. We will insert 7, which is greater than 6. And now we will insert 8. How we will go about 8? Same story. We have to split the tree. So now what will happen is the middle portion is 6, that will go up. So in this case, 6 will become the new parent. So let me edit this tree. We will have 6 here. That is the new parent. And in rightmost tree, we will have 7 and 8. You see how did we make all the values lesser than 3 are 1, 2. Then values greater than 3 and lesser than 6 are 4 and 5. Then values greater than 6 are 7 and 8. Next, we have to insert 9. So for 9, we will make this as here. New value. Then we will insert 10. And then we will insert 11. Now 11 is the fifth value. Same drill, we need to split the data. We will move the center value on top. In this case, which is the center value? Yes, 9. So we will move 9 above, and the new children will be 7, 8 and 10, 11. So let me make the new table. It will be 3, 6, 9. We will have the children as 1, 2, the center children as 4, 5, children 7 and 8, 10, 11. These are the children which we have. Now we need to insert 12. So 12 will be inserted to the next of 11. You'll have 13. And now the fifth element, that is 14, has to be added. We'll do the same split now. To make the 14 happen, we'll find the center of this tree. 10, 11, 12, 13 and 14. Which one is the center? 12th. So we'll move 12 up. We will add 12 here. This will be the new root. Split the existing keys. So in this case, I will remove, let me remove them, and I will make a new table now. It will be 10, 11. Let me remove this, and here we will be 13, 14. We have made new children now here. Now we will add the next numbers, 15, 16, and the fifth one is 17. Same drill, we will add the key. But in this case, now you see how many children are there. 1, 2, 3, 4, and 5th. We have reached the max number of children a parent can have, that is 5. In this case, we will move one step above. You got the point. Now what will happen is, we will move first 15 to the top. Here, we'll add 15 here. Find the center of 3, 6, 9, 12 and 15. That is 9. The new root will be 9. We will move 9 up. The children will be 3, 6. Right children will be 12, 15. Then we will construct the leaf level children. In this case, we will have 1, 2, 4, 5, 7, 8, left of 12. What will be now the left of 12? Now that is a tricky question for you guys. So we will have here as 10, 11, 12 we already have. We will have 13, 14, and then 15. 15 will be the new root, and the right of 15 will be 16 and 17. We have a new tree now and a much bigger. Now the levels have increased to 3 from 2. Next we will add 18 here, then 19. We have 4 children. Now we need to add 20 to the table. So once we add 20, again the same drill will happen. We need to move 18 up. Let's move 18 up in this case. Now we have 9, 3, 6, 12, 15, then 1, 2, 4, 5, 7, 8, 12 will have left child as 10 and 11. Then we will have the right child as 13 and 14. Now we need to move 18 up. So we will move 18 here. Okay. We will have the new children as 16, 17, 19 and 20. Do you see the auto balancing of this B tree? So this is how the roots are automatically moving up. The leaves or the values are moving bottom up. So this is the basics for B plus tree. Now I will tell you how a B plus tree is derived from a B tree. One of the major advantages of B plus tree is that all the nodes are interlinked. So let me write it down. For B plus tree, we have a linked list. All the nodes in this case are internally linked. And one more thing. One is that leaf nodes are linked. Another is that all the values are on the leaf node. You see in B tree, they are on the internal node as well. We have values at the root, but in B plus tree, we make sure that all the values are on leaf. So I'll write down the second property. All the values are leaf. Okay, let me show you an example how a B plus tree works and how it is an improvement over the existing B tree. The property are similar. Okay, let's go down. Okay, I already made this example for you to make it a bit quicker. So we'll go through this, okay? So we will take b plus 3. The max number of children will remain m. The minimum number of children here will be m by 2 ceiling. The number of keys maximum will be -1. The min number of keys will be m by 2 ceiling -1. So you see that how all the values are linked. There is one more property. Since we have to make sure that all the values are on leaf, we do a small redundancy. You see in this tree, this is a typical B tree, B plus tree, sorry, my bad. So in a B plus tree, the 20 here is repeated even after here. The 40 on the root is repeated here. That is a difference between a B tree and a B plus tree. We make sure all the values are in the leaf. And to make that happen, we copy the value from the root to the leaf. Now, if I want to insert some value, let's take an example. I want to insert 25. So how do I insert 25? First, I will check the value where I need to insert. Since these are in ascending order, I will see that 25 lies between 20 and 40. I will go inside here and then I go to the children. In the children, I see they will lie between 20 and 30. In this case, so we have 20 and 40. Those are the root. We'll go bottom. We'll see that they have to be inserted between 20 and 30. We will add the value between 20 and 30 here. And it will become like this. This is the new child or new leaf node. The other leaves will remain intact. Let me make it here. And 5, 10. They have to be linked now. Okay. I hope it makes more sense now. So this is how the insertion happens. Small differences. One is that all the leaf nodes are linked, and the second difference is that we have a redundancy, that we insert even the root values into the leaf nodes so that we don't have to go back to the parent to find the value and find the ranges. So this is how usually a B plus tree works. So the plus means all data is in leaf nodes and leaf nodes are linked. Regular B tree store all the data at level. B plus tree said, nah, let's make the range queries amazing. Now, where do we use B plus tree in real-time environment? Databases like MySQL, Postgres, SQLite, Elephant, all of them uses B plus tree for indexing. Now we create index and makes the search faster. They're also used in file system databases like X4, NTFS, HFS. They all are using B plus tree variants to organize file metadata. When you search for a file, you're traversing a B plus tree without even knowing it. Sometimes they're also used in in-memory databases. Let's compare how the B plus tree and B tree work. So the max children are same. We have the M. Minimum children remains the same, M by 2. The max key is same, M minus 1 and M minus 1. Minimum keys per node, M by 2 seal, minus 1. The data location changes. The data location on B plus tree is leaf only, whereas the data location of B tree is on every node. Let's discuss when not to use B plus tree. So B plus tree are amazing, but they're not always the answer. For example, if you only do exact key lookups, a hash table might be a better, simpler and faster to use than a B plus tree. What if your data fits in memory and you need speed? You can consider skip lists or hash maps in that case. It will be better. And if you need to do concurrent writes constantly, B plus tree locks can be contentious. Though modern DBs have gotten smarter about this, but yeah, you should not use B plus tree in that case. That said, for 95% of the database use cases, they use B plus tree. Let's do a recap of why B plus tree are absolutely legendary. First is they have logarithmic search time. It is way better than binary search trees in terms of the constants. They are self-balancing, no maintenance needed. Amazing for range queries. You can do range queries easily because they have linked list now. All the values are on leaf now. They are disk friendly because the trees have become shorter and wider. So we need fewer discretes. They can be done in shorter space. Then they have a predictable performance. Some of the trade-offs which I was thinking is they are more complex than the simple data structures. They cause write amplification during the inserts and delete. They take more space than the minimal structures. B trees are why our database doesn't catch fire when you ask it to find all the orders from the last month. That's why file systems can quickly locate your embarrassing photos from early 2009. They are the unsung heroes of modern computing. Guys, if you found this video helpful, smash like button, subscribe, drop me a comment if you use any other data structure for indexing. Thanks for watching and remember, stay balanced.